Greetings, mathletes. Today we're going to be learning about improper integrals. So an improper integral is an integral that involves infinity as one or both of the limits of integration, and they're going to be definite integrals. Okay? So definite integrals basically involving infinity are improper integrals. And in this video we're going to be focusing on type 1 integrals. So type 1 improper integrals are actually integrals where one or both limits of integration are either infinity or negative infinity. Okay, so one or both limits of integration are infinity or negative infinity. Okay, that's a type 1 improper integral. Now, a type 2 improper integral would be covered on a different video. I don't know if I'm going to do it for this class. If I have time, I might make another video on that. But just so you know, type 2 improper integrals don't actually have infinity or negative infinity as a limit of integration. Rather than that, they actually have a point where the function is undefined, which is a little bit different. Okay, but here we're focusing on basically infinite integrals, definite integrals involving infinity. Okay, so let's see an example of calculating an improper integral. So for our first example here, the first thing they say is the integral in this exercise converges. Alright, that's interesting. So those aren't really directions, those are just telling you something. Now we haven't talked about convergence or divergence a whole lot yet. You might remember that from one of your other math courses though. When they say that the integral converges, basically that means that after you calculate it, it's going to be a real number, okay? Because we're doing a definite integral. So here in this context, the word converges just means that the answer is a real number. And that's not a very precise definition. It's actually a lot more complicated than that. But for our purposes here, for improper integrals, when they say that it converges, that basically just means that after you calculate the integral, you're not going to end up with infinity as your answer, and you're not going to end up with negative infinity as your answer, and you're also not going to end up with indeterminate or undefined. None of that. Okay, so the answer is actually going to be a number like pi over 2 or 7. Okay? So that's what they're saying there. And then let me read the rest of the directions. So the rest of the directions say evaluate the integral without using a table. Okay? Evaluate the integral without using a table. Now, the without using a table part is completely optional. I do not have a problem with you using a table, so don't really pay any attention to that. I'm just copying down the directions that they have on your homework. They don't let me change them on my math lab. But you can basically ignore the part where it says without using a table. I'm just going to cross that out. Okay, so it shows up in the directions, but you can basically ignore it. However, we're not going to learn how to use a table. So the way I'm going to teach it to you is we're going to do it by example. And the basic idea is if you have infinity or negative infinity as one of your limits of integration, you're going to do the whole problem the way you normally would. You just integrate normally. But at the very end, when you have infinity or negative infinity, instead of plugging them in, you rewrite them as a limit. Okay? You rewrite them as an infinite limit, but you're still going to use the fundamental theorem of calculus. So it's actually not that hard. Most people find these pretty fun. At least I do. Okay, so example number 1, we're going to be doing the integral from 2 root 3 over 3 to infinity. Okay, the integral from 2 root 3 over 3 to infinity. Sorry, I can't write that small very well. Okay, so from 2 root 3 over 3 to infinity of dx over x squared plus 4. In fact, let me zoom in just to make it easier for myself. Because I'm writing kind of small there. It's getting a little bit hard to write. Okay, so we have the integral from 2 root 3 over 3 to infinity of dx over x squared plus 4. Okay, and basically all we have to do here is we're going to do all the steps we would normally do. So we're going to calculate the antiderivative, and then at the very end, rather than plugging in infinity, we're going to be writing it as a limit. But we don't have to worry about that until the end. Okay, so first of all, we have to calculate the antiderivative of dx over x squared plus 4. So if you go to your formula sheet, that's the best way to do it, unless you have them memorized, which most people don't. So if we go to the first page of our formula sheet, and we look for, here we want the integral of, it's really 1 over x squared plus a squared. Okay, so this is 1 over x squared plus a squared. Okay. So that's what we've got there. And so what's in that format? Well, we look under antiderivatives, and the closest one is this one right here. The integral of 1 over a squared plus u squared is equal to 1 over a tan inverse of u over a plus c. Okay, so I guess I should be writing it as u squared plus a squared. Okay, so here we can see that u equals x, and then a equals the square root of 4, which is 2. Okay, so that's going to mean du equals dx. Okay, so really what we're integrating here is we have the integral of 1 over, if we write it the same way they did, we have 1 over a squared plus u squared, and then because du equals dx, this whole thing is du. So the integral of 1 over a squared plus u squared du, going back to our formula, is 1 over a tan inverse of u over a plus c. But we don't need to write the plus c because this one's a definite integral. Okay, so 1 over a tan inverse of u over a. One over a tan inverse of u over a. And of course in this problem we said that u equals x and a equals 2. Okay, so plugging in here, we have 1/2 times tan inverse of x over 2. All right, but then we don't write a plus c, of course, because this was actually a definite integral. We had these limits of integration, so they were going from x equals 2 root 3 over 3 to x equals infinity. Okay? So now here's the interesting part. At the very end here, we're going from x equals 2 root 3 over 3 to infinity. And the thing is, you can't really plug in infinity, or at least you're not supposed to. Some people do it anyways, and it usually works okay. But I'm going to teach you the correct way to do it anyway, just so that we know the correct way. So the correct way to do it is instead of writing infinity here, we're actually going to end up writing it as a limit. Okay? So, if you want to just plug it in, that's fine, but it's going to look a little weird. So if I go ahead and factor out the 1/2, then I'm going to have 1/2 times, if I plug it in directly, I would have the top number, so tan inverse of infinity over 2 minus tan inverse of 2 root 3 over 3. The thing is, you're not really supposed to write tan inverse of infinity over 2. So let me write that down for your notes. Okay, you're not supposed to write it this way. So this isn't not written correctly, is what I want to say. I mean, some people can just write it that way, but it's not really 100% correct. So what you're supposed to do is you're supposed to write as a limit. Okay? And when I say it's not written correctly, another way of saying that is it's not written properly. Okay? Not written properly. And lo and behold, what we're doing is an improper integral, so it makes sense that it's not written properly. So this part, I'm going to put quotes around it, the tan inverse of infinity over 2, because that's not really how you're supposed to write it. Okay? So the way you are supposed to write it is, instead of writing the infinity over 2, instead of writing infinity there, you're supposed to pick a variable. So it doesn't matter which variable you choose. Most people choose either a or b. So here I'm just going to rewrite this as the limit as b goes to infinity of tan inverse of b over 2. Okay? So now the way I have it written in blue here, this is actually correct. This is the way you're supposed to write. When you're plugging in infinity, you're not really allowed to plug it in. You have to write it as an infinite limit. Okay, but that's just a detail. Some people get away with just writing it this way, and that's fine. Okay, so what we got here is we still have a 1/2 out front. So we have 1/2 times bracket limit as b goes to infinity of tan inverse of b over 2 minus tan inverse of 2 root 3 over 3. And I think I forgot something up here. So remember, it was actually tan inverse of x over 2. So I should have, over here, I should have tan inverse of 2 root 3 over 3 over 2. Sorry about that. Because remember, the function was actually tan inverse of x over 2. So over here I got infinity over 2, and over here I should have 2 root 3 over 3 over 2. Okay, but for that one, we can see that we have a 2 down here on the bottom. So if you multiply by the reciprocal there, you're going to end up multiplying by 1/2. So in other words, something's going to cancel out. All right. So in other words, what I'm saying is this is going to be 2 root 3 over 3 times the reciprocal of 2, which is the reciprocal of 2 over 1. So that's going to be times 1/2. I'm just writing it out because some people have trouble with fractions. They get confused when they see something like 2 root 3 over 3 over 2. I know it can get a little confusing sometimes. Okay, so, all right, so we're good so far here. And then here's the little bit tricky part. So over here, these 2's are going to cancel out. And we should all be able to do tan inverse of root 3 over 3. So if we do the right part, we can just do that using a unit circle. So for tan inverse of root 3 over 3, remember that tangent of theta equals y over x. Okay? And here that's equal to root 3 over 3. But remember, root 3 and 3 are not really things that show up on the unit circle. So what you do is you can divide the top and the bottom by root 3 to make it more like something that would show up on the unit circle. Okay, so on the top we get root 3 divided by 3 is 1. And then on the bottom, 3 divided by root 3 is actually just going to be root 3. Okay? And the reason that's true is remember that 3 is the same as root 3 squared. So the square cancels out down there with the root 3. So we just get root 3. So this is 1 over root 3, which is the same as 1/2 over root 3 over 2. Okay, and because of the way tan inverse works, we wouldn't have them both be negative. So x and y are both going to be positive here, because that's the only way they would be in the range of tan inverse. Okay, so we're looking at y is 1/2, y is 1/2, and x is root 3 over 2. And of course, if you have a calculator that will just do tan inverse of root 3 over 3 and give you an exact answer, that's even faster. Actually, it's a lot faster. Okay, so what do we got here? X is root 3 over 2, y is 1/2. So going to our unit circle, zooming in. X is root 3 over 2, y is 1/2. So we're at pi over 6. Okay. All right, so that means tan inverse of root 3 over 3 is pi over 6. So going back here, we're actually going to be subtracting, let me erase this. We're actually going to be subtracting pi over 6. Okay, so minus pi over 6 there. And then here's the really tricky part. How do you do limit as b goes to infinity of tan inverse of b over 2? Probably the easiest way to do this is, unless you have your inverse trig functions sort of pictured in your head, would be to use either a graphing calculator or an online graphing utility like Geogebra. So I'm going to show you how to use Geogebra here. So basically the easiest way to do this is to just look at the graph of tan inverse of b over 2. Okay, so let's do that for the blue one. So use graphing utility. And remember, for my course, I let you use basically anything. So if you don't have a graphing calculator, just use Geogebra like I'm going to use in this video. So basically you go to Google and you type in Geogebra graphing calculator. Okay? And then it's the first link here, Geogebra graphing calculator. I think I might have talked about it in another video. I don't know if you remember that one. But basically up here in the top left corner, you're going to want to type in your function. So in our case, we're going to be typing in tan inverse of x over 2, because b is really just a variable, so we can write x over 2. Okay, so we're going to have tan inverse. So you press the little exponent button, which is down here, and then tan to the -1. And then you go back out of that with the right arrow on your keyboard, and then you type in parentheses, and then you go ahead and type in x over 2. Okay, and then the way it's written, notice that the y-axis is actually counting in whole numbers, which we don't want. It's counting in integers. What we want is we want the y-axis to be counting in pi, because remember, we're looking at a trig function, so our answer is probably going to be in terms of pi. So how do we look at it and get it so that we can see what the function is approaching? Well, we go to settings up here in the top right corner, looks like a little gearbox, and then we click on settings here, and then we go to y-axis, because the y-axis is the one we're actually concerned about here. And then under unit down here, we click on unit, and then we click on pi. All right, and then we just go ahead and close this, and then you can drag this over. So if we want to find the limit as x goes to infinity, that means, well, what is this function approaching as we go further and further to the right here? Well, as we can see, now that the y-axis is labeled in terms of pi, we can see that this is pi over 2, right? Because this is halfway between 0 and pi. So it looks like it's approaching pi over 2, but we can just scroll to the right to be sure. And as you can see, the further I go, the closer it's getting to halfway between 0 and pi, which is actually pi over 2. Okay? So that's one nice way of calculating an infinite limit for a strange function like an inverse trig function, is to just do it graphically. So the limit as x goes to infinity of tan inverse of x over 2 is pi over 2, because infinity goes to the right, right? So positive infinity is to the right. Okay? So that means the limit as b goes to infinity of tan inverse of b over 2 is going to also be pi over 2. Okay? So what we got there is we have a pi over 2 minus pi over 6, and then don't forget we still have a 1/2 out front. Okay, so we have 1/2 times pi over 2 minus pi over 6. Okay, and then of course we can build these to a common denominator. So for pi over 2, if we multiply that one by 3 on the top and the bottom, then we're going to go ahead and get 3 pi over 6. Okay, so we have 3 pi over 6 minus pi over 6, and then we have a 1/2 out front. And we know that 3 pi over 6 minus pi over 6 is 2 pi over 6. Okay, so we have 1/2 times 2 pi over 6. Right? Okay, and I feel like I missed something here. What did I miss? So let's see, we had a 1/2 out front. Oh, that looks correct. Sorry, I'm just looking through my notes real quick here. Actually, I'm going to pause it for a second. Okay, so I looked over my notes, and I actually was correct on everything we did here. So I shouldn't have been doubting myself. So what we got here is 1/2 times 2 pi over 6. And then the 2 on the top and the bottom can cancel out. So we're just left with pi over 6. And for some reason on the view an example on my math lab, they got pi over 3 here, but that's incorrect. That's a typo. Usually their view an example is very accurate, but here they actually got the wrong answer. Okay, so here our answer is going to be pi over 6. Pretty cool, huh? So that's an improper integral. All right. All right, so I kind of took my time with that one, so I want to do a few more, but I'm going to try to pick up the pace a little bit. Okay, so that was example number 1. Okay, next is example number 2. So example number 2 has the same instructions. Okay, evaluate the improper integral. And here we're doing the integral from 1 to infinity of 1 over x to the 1.00004 dx. Oh my goodness. So let's make sure I copy down the right number of zeros. So again, that's 1 over x to the 1.00004. So a total of 4 zeros there. Now this can look a little bit intimidating or confusing for some people because they just don't know what to do when they see a decimal or a fraction or whatever. But this is actually really easy to do the antiderivative. So what we can do is instead of writing it as 1 over x to a positive exponent, we can rewrite it as x to a negative exponent. In other words, we just go ahead and move this power to the numerator, and then the exponent becomes negative. Okay, so it becomes x to the negative 1.00004 dx. Okay? And then to go ahead and find the antiderivative here, because it's just a power, we can use the power rule. So remember, the power rule for integrals says that you add 1 to the exponent and then you divide by the new exponent. So here we're going to be getting x to the negative 1.00004 plus 1 divided by negative 1.00004 plus 1. So all I did there was I added 1 to the exponent and then I divided by that new exponent. And hopefully you're good enough with decimals to do this in your head, but if not, you can use a calculator. But it shouldn't be too difficult. So basically here, 1 minus 1.00004, well, the ones are going to cancel out, and you're just going to have negative 0.00004. Okay, so you have x to the negative 0.00004 divided by that same number. So divided by negative 0.00004. But remember that this one's actually a definite integral. So we're going from x equals 1 to x equals infinity. Okay, so we're evaluating this from 1 to infinity. And let's see, for this problem, do they want us to round at the end? Oh, I guess we're not going to end up needing to round at the end. Okay, so we don't have to worry about that. However, even a very simple calculator could be helpful here. But I'm going to go ahead and factor out this negative 0.00004 out front. But remember, it's actually in the denominator. It's not in the excuse me. It's not in the numerator. So we actually have a 1 over negative 0.00004. And then we're evaluating x to the negative 0.00004 from x equals 1 to x equals infinity. And I'm just going to use a calculator here. So what is 1 divided by negative 0.00004? Well, I'll just use the calculator that comes with the computer, because everyone has one of those, right? Okay, so 1 divided by 0.00004 gives us 25,000. Probably could have done that, but calculator's faster for that. Okay, but there's a negative there, so it's going to be negative 25,000. So we have negative 25,000 out front, and then plugging in here, we're going to have infinity to the negative 0.00004, but I'm going to put quotes around that because that's not proper notation. You can't have infinity raised to a power or really anything like that. You're not supposed to plug it in like that. However, it's still fun to write it that way, even though it's not correct. Okay, and then if we subtract, we're gonna be I can't talk. We're gonna subtract 1 to the negative 0.00004. And you might be wondering, well, Well, why do they have these silly decimals here? Well, in the real world, decimals are actually really common, so it's good to get some practice with them. Okay, so let's deal with this problem here that I put in quotes. So remember, that's improper. The way it's written is not proper. So we have to write it as a limit. So instead of writing infinity raised to that power, we're going to rewrite it as an exponential. So we're going to write it as b is what we used last time. So let's use b. So it's going to be b to the negative 0.00004. And we take the limit as b goes to infinity of that. So very similar to the last problem. And then don't forget we still have a negative 25,000 out front. And then over here, we can go ahead and calculate 1 to the negative 0.00004. Well, what's 1 to any power? 1 to any power is 1. But if you don't believe me, type it into your calculator. You do 1 x to the y, and then, let's see, where's the negative button? Negative 0.00004. Okay, I did not do that right. I'm not very good with this calculator here. I think you have to do it in the opposite order. Okay, so first we're going to do clear. Okay, so 0.00004. Change it to a negative, and then I do x to the y to the 1. Dang it, I messed up again. I'm still going to leave it on the video. Okay, so I think I was doing it correctly the first time, I just didn't type it in right. So I do 1 x to the y, and then I do, let's do parentheses, maybe that'll fix it. Parentheses, 0.00004, and then negative. That fixed it. And then I end parentheses, and then I press equals. Yes, that's 1. So all that to just summarize what I just said, which is that 1 to any power is 1. Okay, so this here is just 1, because 1 to any power is 1. But there's a minus in front of it, so it's actually going to be a negative 1. Okay, so this problem is kind of interesting. It's actually not that difficult, but it's a little bit technical. I guess it's got a lot of technical things going on here. Okay, so we still have a negative 25,000 out here. And then now we need to do this limit. So probably the easiest way to do this limit is to rewrite the negative exponent as a positive exponent. Okay, so I'm going to rewrite this as the limit as b goes to infinity of 1 over b to the 0.00004. Okay, and as you can see here, in the numerator we have 1, which is a fixed constant, but in the denominator, if we plug in infinity here, plug in infinity, this denominator is actually going to be infinity. Okay, so that denominator is going to go to infinity, because even though it's raised to the 0.00004 power, it's still going to go to infinity. It's still going to go to infinity. Excuse me. But the numerator is a constant. So here we actually have 1 over infinity, and 1 over infinity actually goes to 0. Okay? So you might not have known that, but that's pretty cool. Okay. So yeah. Basically, if you have 1 over infinity, that goes to 0. Because your numerator is fixed, but your denominator is becoming infinitely large. And if you don't believe me, just look at 1 over x in a graphing calculator and look as x goes to infinity on the right side, you're going to see that 1 over x is approaching 0 as a horizontal asymptote. Okay, so that limit is just 0. Okay, so really all we have here is negative 25,000 times 0 minus 1. Okay, we don't need that 0. The negatives cancel out, and 25,000 times 1 is 25,000. Okay, so here our answer is actually just going to be 25,000. So that's kind of a weird problem, but it's a good thing that I did it on this video just to make sure that you are able to do these kinds of problems on your own. Okay, so let's continue onward. Continue onward. So I think I just want to do one more example of a type 1 improper integral, since that's all we're doing on this video is the type 1. So this next one is another indefinite integral, but it has a slightly different setup. Okay, so example number 3. Example number 3 is the integral from negative infinity to negative 9 of 64 over x squared minus 64 dx. So of course, first we want to actually just do the integral part of it, in other words, the antiderivative. And in order to do that, we'll look at our formula sheet for something in the form x squared minus a squared or u squared minus a squared. So let's see if we can find something in the form u squared minus a squared on our formula sheet. Oh, let me zoom out. So that would be under the first page under integrals. Okay, so we're looking for a u squared minus a squared. And unfortunately, we are out of luck. So we don't have anything in the form 1 over u squared minus a squared. So remember, this one is 1 over a squared plus u squared, and that gives us tan inverse. But here, we don't have a minus there. And we have this one over here, but this one has a square root. So we don't have it in that form. So there's a couple ways we could proceed. One way would be maybe you could do a trigonometric substitution here. But I think it would probably, the easiest way to do this problem is by partial fractions. At least that's the way I'm going to do it. Okay, so we're going to expand by partial fractions. Because the way it is, I can't really do this integral. I can't do a u substitution, and it doesn't show up in our formula sheet as one of the forms that we can use. And again, you might be able to do a trigonometric substitution, but I find partial fractions to usually be easier for this kind of thing. Okay, so in order to do partial fractions, hopefully you've already watched my other 2 videos on that. In order to do partial fractions, you first need to factor the denominator. Okay, so this denominator right here, we need to factor. Okay, and remember, it's the difference of squares. So this is the same as x squared minus 8 squared. So the way that's going to factor is it's going to be x plus 8 times x minus 8. Okay, x plus 8 times x minus 8. Or depending on what book you use, it might be x minus 8 times x plus 8. The order doesn't really matter. But what matters is that you actually factor it correctly. And we still have a 64 on the top. Okay, and then what we're going to do from here is we're going to go ahead and set this equal to capital A over the first factor, so capital A over x minus 8, plus capital B over the second factor, so that's capital B over x plus 8. Okay, and then what we want to do is we want to build all of these to the same denominator. Okay, so for the first fraction on the right side, I can see that I am missing an x plus 8 from the denominator, so I'm going to build this one by multiplying it on the top and the bottom by x plus 8. Okay, so on the right side we have a times x plus 8 excuse me, over x minus 8 times x plus 8. Okay, and then we have plus b times the quantity x minus 8 over x plus 8 times x minus 8. So as you can see there, just like in my other videos on partial fractions, basically I'm just building all these to a common denominator, and so I'm multiplying each of the fractions on the right side by what's missing on the top and the bottom. Okay, so for the first fraction we were missing an x plus 8, so I multiplied by that. And in the second fraction we were missing an x minus 8, so I multiplied on the top and the bottom by that. Okay, and then on the left side we already have the whole denominator that we need. So we already have an x minus 8 times x plus 8. And then the nice thing about doing it this way is now that we built everything to a common denominator on both sides, we can basically just cross out all the denominators. So all the x minus 8, x plus 8, all of those just cross out. Okay? And so what we got here is we have 64 equals capital A times x plus 8 plus capital B times x minus 8. All right, and then on the right side, we need to go ahead and distribute. So we're going to go ahead and distribute the A and then also distribute the B. And remember, A and B are unknowns, but they're actually constants. Okay, they're not actually variables. So at the end of the problem, they're going to be numbers. They're going to be real numbers. Okay, so after distributing here, we have 64 equals ax plus 8a plus bx minus 8b. Okay. And then remember, when you're doing partial fractions, you have to equate the powers on the left and the right side. So equate like powers, which basically just means you equate the coefficients or the constants of each power. So on the left side here, we have 0x plus 64. So if we equate the powers that are x's, so we have 0x equals ax plus bx. But you're actually only equating the coefficients, you're not equating the x's themselves. Okay, so that's going to be giving us our first equation is 0 equals a plus b. And again, if any of this is going over your head, make sure you watch my other videos on partial fractions. Those are before these. Okay, and then from here, we still need to equate the constants. Okay, so we have 64 on the left side equals 8a minus 8b on the right side. Okay, so 64 equals 8a minus 8b. Okay, so we have 0 equals a plus b, and 64 equals 8a minus 8b. Now what do we do from here? Well, if you watch my other videos on partial fractions, now you need to actually solve and figure out what A and B are. Okay, so we solved this system of equations. Now with this one, probably the easiest way to solve it for me would be just doing the addition method. So I'm going to go ahead and multiply the top equation on both sides by 8. So if I multiply the top equation by 8, then my system is now going to be 0 equals 8a plus 8b. And then our bottom equation is still 64 equals 8a minus 8b. And as you can see, I multiply the top equation by 8 so that the 8b and the negative 8b are going to cancel. Okay, so when we add straight down here, the 8b and the negative 8b cancel out, and then 8a plus 8a is 16a. 16a. So we have 64 equals 16a, and then we can go ahead and divide both sides by 16. So we get a equals 64 divided by 16, which is 4, right? So a equals 4. And then to find b, we can plug in a equals 4 into one of the original equations and solve for b. Okay, so looking at these original equations, I'm going to choose the top one before we multiplied by 8. So I'm going to plug in 4 for a in the top equation. Okay, so that was before we actually multiplied by 8. So it was just 0 equals a plus b. Okay, so this top equation is now going to become 0 equals 4 plus b. And then if we subtract 4 from both sides, we get b equals negative 4. b equals negative 4. Pretty cool, huh? Okay, so we got a equals 4 and b equals negative 4. So now we can go and plug these in to our partial fraction decomposition. Okay, way up here. So I already forgot them, but I think we said, did we say a was negative 4 and then b was positive 4? I don't know, I'll just check it in a second. So we're plugging in a and b, whatever they are, up here. So let me just make sure I remember them right. So let's see, was a negative 4 and b positive 4? No, I got them mixed up. Okay, so a was positive 4 and b was negative 4. It's probably because I haven't eaten lunch yet. Okay, so a was positive 4 and b was negative 4. Okay, so we plug those in to our partial fraction decomposition. So remember, we're just plugging in a and b. That's the whole point of this, was to rewrite it as two fractions. And now these two fractions are going to be a heck of a lot easier to integrate than the original problem, which was pretty tough to integrate the way it was written. Okay, so keep in mind that these two we can now distribute the integral symbol to. Okay, so we still have an integral here. So we have the integral of the first one, dx, plus the integral of the second one, dx. Probably should give myself some more room here. It's looking kind of messy, so let me rewrite it. So we have the integral of 4 over x minus 8 dx plus the integral of negative 4 over x plus 8 dx. And we don't really need those parentheses in the denominator anymore, so I'm going to get rid of those. Okay? And both of those are definite integrals, but I'm not bothering to write that until the very end. So for the first one, if we factor out the 4, which is a constant, then remember the integral of 1 over u du is just natural log of absolute value of u. Okay? So what we're going to have here is we're actually going to have 4 times natural log of absolute value of x minus 8. Okay? And if that went over your head, again, I did examples like this in an earlier video on partial fractions, so make sure you watch those first. Okay, so we have 4 times natural log of absolute value of x minus 8 plus, over here we have a negative 4 that I can factor out front. So I guess instead of writing a plus, I should be writing a minus. So we have minus 4 times natural log of absolute value of x plus 8. Okay? All right, and then I wish we could combine these. I don't think we really can. Nah, I don't think we can combine them, so to speak. So we're just going to go ahead and plug everything in. Okay, so remember the original limits of integration here? We're going from negative infinity, so negative infinity, to negative 9. So x goes from negative infinity to negative 9. All right, and so we're going to just go ahead and plug in. So it's going to be a bit of a mess. So plugging in negative 9, which is the top number, we have 4. Well, actually, we could just bring the 4 out front to make our lives easier. So if we bring the 4 out front for all this, both of those 4s, we're going to have 4 times bracket, and then we're going to have natural log of absolute value of negative 9 minus 8 minus natural log of absolute value of negative 9 plus 8. Okay? And then we have to subtract the entire function evaluated at negative infinity. So now we're going to be doing minus natural log of absolute value of negative infinity minus 8 minus natural log, so I should put parentheses around this, minus natural log of absolute value of negative infinity plus 8. And of course I should put quotes around these because you can't really plug in negative infinity or positive infinity like that. That's not allowed. It's improper. Improper math, just like improper English. Okay. But if we rewrite those as limits, they're not going to be that bad. And then up here, for these ones, for the numbers, they're pretty easy. So negative 9 minus 8 is actually negative 17. Okay? So up here we have negative 9 minus 8 is negative 17. And it's natural log of absolute value of negative 17. And the absolute value of a negative number is just the positive version of the number. Okay, so that's actually going to be ln of 17. And then over here, we have minus ln of absolute value of negative 9 plus 8. Well, negative 9 plus 8 is negative 1. And absolute value of negative 1 is just 1. And we know that e to the 0 is 1. Okay, so we actually have minus ln of positive 1, and that's just 0. Right, because e to the 0 is 1. All right, and then for the other part of it, the infinite part, we can go ahead and rewrite those as limits. So we have minus parentheses limit, as, this time I'm going to use a because it was the bottom limit of integration. Limit as a goes to infinity of ln of absolute value of a minus 8 minus the limit as a goes to infinity of ln of absolute value of a plus 8. Okay. Actually, let me scroll down here so we can see what's going on. Whew, a lot going on there. Okay, so if you're not sure what that is, you're welcome to use a grapher. But if you are sure what it is, then you might be able to kind of, do it in your head. So what's going on here is if you look at a grapher, we're looking at natural log of absolute value of x. Okay, so let's see what that one looks like. Okay, so Geogebra graphing calculator. Let's delete our tan inverse one. And now we're going to type in natural log of absolute value of x. So what does that one approach as we go to infinity? What is that one approaching? Well, even if we change our unit, I changed my unit from pi to just 1, we can see that this, as we go to positive infinity, the function just keeps increasing. So that's going to infinity. And then if we go to negative infinity, which is actually the one we were supposed to be looking at, that's going to the left. We can see that the function keeps increasing as well. So those actually go both to infinity, which is not proper. So we got to be a little bit more clever here. So let's try to get a little bit more clever here. What can we do here? Well, one thing we could do is, remember, if you're subtracting outside of a logarithm, that's the same as dividing inside of the logarithm. So I think that might be the best way to do this. Because the way it's written, these are both going to go to infinity. So this one goes to infinity, and that one goes to infinity. So you actually get infinity minus infinity, which is indeterminate. And we don't want indeterminate. That's not our answer. So if you get indeterminate, that means you haven't finished it yet. Or as I like to say, it's called indeterminate because you have not determined the answer. Okay, so what we're going to do here is we're actually going to factor out the limit here. And we'll go ahead and distribute the minus while we're at it. All right. So up here we have a 4 times ln of 17. And then distributing the minus. Since we got indeterminate, we're going to have to do something. So we distribute the minus, and we get a negative limit as a goes to infinity of ln of absolute value of a minus 8 plus limit as a goes to infinity of ln of absolute value of a plus 8. Okay. And like I was just saying, other than distributing the minus, we can go ahead and factor the limit outside of it. Since both of them are the limit as a goes to infinity, we can actually factor this out here. So we can factor both of those out. All right, let me zoom out so that we can see all this. So because we got indeterminate, that's why I'm having to play these games. Okay, so what we have here is a 4 times bracket ln of 17 And then factoring out the limit, we have plus limit as a goes to infinity of parentheses negative ln of absolute value of a minus 8 plus ln of absolute value of a plus 8. And if we go ahead and switch the order around in there, that's going to be ln of absolute value of a plus 8 minus ln of absolute value of a minus 8. Okay, now here's the tricky part. Why did I factor out the limit? Well, we got indeterminate, so we have to do something, right? We got to be clever in some way. Well, the reason I factored out the limit is now because I'm subtracting outside of a logarithm and we have the limit factored out front. Remember, subtracting outside of the logarithm is the same as dividing inside of the logarithm. And the order is left to right, top to bottom. Okay, the order does matter when you're dividing or subtracting. Okay, so this is going to be ln of absolute value of a plus 8 divided by absolute value of a minus 8. Okay, so now I can actually write it as a single limit here. And then we still have a 4 times bracket ln of 17 plus that. Okay, so that's using one of the properties of logs. It's called the quotient rule. If you're subtracting outside of the logarithm, that's the same as dividing inside of the logarithm. So now here, we can kind of do a trick, which is, first of all, we could just plug this all in to our graphing calculator. That would be one way of doing it. Another way of doing it would be to multiply the top and the bottom by 1 over a. Okay, and I think I'm actually going to do it that way, so we don't even have to use a graphing calculator. Okay, so the trick here would be, I can actually just write this entire thing in an absolute value. Okay, and then if I multiply the top and the bottom by 1 over a, and then I distribute that, then that's going to allow us to take the limit. Okay, and I'm allowed to multiply the top and the bottom by 1 over a, because 1 over a over 1 over a is just 1. Okay, and I'm going to be kind of just ignoring the absolute value for now. I guess I could write 1 over absolute value of a or whatever, but it's not that important. So anyway, what we got here is, on the top, we're going to have 1 plus 8 over a. And then on the bottom, we're going to have 1 minus 8 over a. And as you're going to see in just a second, we're not even going to need these absolute values anymore. Because if I take the limit as a goes to infinity of this, well, the 8 over a on the top is going to go to 0. And the negative 8 over a is also going to go to 0 on the bottom. Oops, I forgot to write ln. So I got so excited that I forgot to write ln. So we have limit as a goes to infinity of ln of absolute value of, well, we have 1 plus 0 over 1 minus 0. Okay, so that's actually the limit as a goes to infinity of ln of 1. Which you should know, e to the 0 is 1, so ln of 1 is just 0. So we did all that work, and it turned out that whole thing just ended up being 0. But that's how it is sometimes in math. You do a bunch of work and it ends up being 0. Okay, so after we do all that, we're going to end up with the correct answer. So I did it right. So because that's 0, we still have a 4 ln of 17 over here. Okay, so we have 4 times bracket ln of 17 plus this limit. But we said that is just the limit as a goes to infinity of 0. Okay, so for our answer, we're actually just going to have 4 ln of 17. Okay, because over here we had 4 bracket ln of 17 plus 0. Okay, pretty cool, huh? So that completes our video on type 1 improper integrals. Thanks for watching.